Everyone, I'm Yiqing Lu from Tsinghua University. Our work is investigating bubble mechanism for recasting to improve 3D target acquisition in virtual reality. So from the title, we can see two important keywords. One is bubble mechanism, and the other is recasting. So this work is to talk about recasting in 3D target acquisition in VR and use the bubble mechanism to improve it. Let's look at these two keywords. So what's the recasting? This is a common term in VR that the user hold a maybe VR controller to cast a ray in the space and use the ray to go through some targets to select them. The ray allows the user to identify a very remote target, but it's difficult for the user when the target is so small, because the user's hand is not so stable and the ray maybe trembles. So many previous researchers paid a lot of attention to improving the recasting. Next, what is bubble mechanism? This term is from the work Bubble Cursor presented by Grossman in 2005. The bubble cursor is a dynamic 2D area cursor, which selects the target with the minimum distance. The range of the cursor changed when the cursor moved to ensure there is exactly one target falls into the range. So the cursor is like a bubble, which expands and shrinks. Actually, the cursor is moving in a Bernoulli diagram and selecting the nearest target in terms of the 2D distance. And our question is, what about the recasting plus bubble mechanism? The bubble cursor is easy to understand, always selecting the target with the minimum distance. However, a cursor has 3 degrees of freedom, but a ray has 5 degrees of freedom. So for recasting, how to define the distance for a ray? There are a common sense of 3D distance. The first is Euclidean distance, that we define the minimum distance between the ray and any point on the target. This is straightforward. Another is angular distance. That is, we define the angle between the ray and the target. So the target with smaller angle will be regarded closer. This definition is common in eye-based or field of view-based interactions. But in our work, the center is on the hand, so there is a parallax. We will consider these two definitions in later studies to show which one is better. Now we start drawing the bubble for the ray. From the bubble cursor, there are two bubbles. One is around the cursor and the other is around the target. In 3D space, we use two semi-transparent spheres to wrap the ray and the target, like this. We invited some participants to evaluate our prototype, and they said two bubbles might block the user's view and make the wrapped target not so clear, and it seems two bubbles are redundant. Then we improve the design by using only one bubble and make the bubble tangent to the target rather than wrapping the target. Our participants thought it's clearer, but sometimes there are a bad case. That is, when the ray is far away from the closest target, then the bubble will become super big. The user can be even inside the bubble. It looks weird sometimes when the bubble is very large. We go further by designing the bubble from a sphere to a disk. The disk bubble is tangent to the target, and from the user's view, it looks similar as the spherical bubble. But it reduces the depth of the bubble and makes it less weird. Our participants thought this design was better, but some of them reported that when the nearest target switches, the bubble also switches. So when you transit from one target to another target, bubble also jumps in space. It's not bad, but the transition should be more smooth. We continue improving the design. We then render the bubble in an infinity depth. With this design, the transition becomes smooth from one target to another. From the user's view, it looks the same as the previous prototype. Actually, it's just like a 2D bubble cursor moving on the sky. Our participants were satisfied with this design and said it is easy to understand and has good user experience. Finally, we add a curve to the selected target to notify the user which one is now selected. So this is our final design of how to render the bubble. Let me show you a video of ray casting with bubble mechanism. We can find that it's really easy to select target because you don't have to accurately go through it. The user holds the controller to move the ray. The selected target is highlighted, and the user presses the trigger button to select it. Selecting very small target or occluded target is also easy because you can use the space around the target to help you. Next, we conduct the first experiment. Our goal is to evaluate the recasting with bubble mechanism in general cases. So-called general cases are scenes without difficulties, that the targets are arranged randomly and sparsely. The task is to select 10 targets with 3 repetitions, totally 30 times in a scene. We have 6 scenes, and we are in 3 depth ranges, near, middle, and far, and 2 target sizes, large and small. Near range is where the user can directly touch targets. Middle range is the room scale range, and far range are only accessed by recasting. We vary the depth and the size to create different types of scenes. And we recruited 12 participants and built a platform in HTC Vive with Unity. We evaluated 7 techniques in this experiment. Technique 1 is 3D bubble cursor, which is the extension of 2D bubble cursor in 3D space. Technique 2 is go-go, which is the virtual hand metaphor. The user controls the virtual hand by stretching the arm. The distance of the virtual hand from the body will be nonlinear function to the position of the controller. The nonlinear mapping allows the virtual hand to grab targets far away from the body. Technique 3 is Naïve Ray. It's the simple and normal ray casting. Technique 4 is Heuristic Ray. Heuristic Ray calculates a score for each target and selects the target with the best score. The score is based on spatial models and temporal models. The spatial model evaluates the relationship between the ray and the target, maybe based on the angle between them. The temporal model provides the accumulation of the scores over a period of time. Note that this score function is always implicit to the user, but our bubble mechanism makes the process explicitly. Technique 5 is a typical two-step technique. In the first step, the user multi-selects targets using a cone-like ray casting. In the second step, the user identifies the desired target within select targets, which we call disambiguation. There are many disambiguation methods, and we choose the squad that the targets are arranged in 4 quadrants and eliminate progressively. Technique 6 and 7 are recasting with bubble mechanism. We call them bubble rays. In terms of the distance definition, we have 2 bubble rays. Bubble ray E for Euclidean distance and bubble ray A for angular distance. Due to the coronavirus situation, we can go back to our lab to record more videos to show how these techniques work. I appreciate you to read our paper and reference if you have some questions about these techniques. So 7 techniques were evaluated. Due to the range of selection, bubble cursor was only evaluated in near scenes, and go-go was only evaluated in near and middle scenes. This is the result of task completion time in all 6 scenes. We can find that Naïve Ray was slow when targets became slow. Other techniques all had a consistent performance in all scenes. And we find bubble ray A always had the least task completion time. A repeated measures ANOVA showed the bubble ray A had a significant higher speed. We also examined the error rate. We found bubble cursor, quad cone, and two bubble rays had a significantly lower error rate. We also measured moving distance, which reflects how long the user moved the controller. We found Naïve Ray, Heuristic Ray, and Bubble Ray A had a significantly shorter moving distance, which indicates the user's hand won't be tired. We also collected subjective feedback from participants using a 7-point Likert scale questionnaire. We asked them on 4 measures. What's the performance of the techniques? Are you tired to use it? Is it intuitive? And the overall performance. We found that Bubble Ray A was again consistently rated the best in all measures, which shows it has good user experience. So we have several findings from this experiment. First, bubble mechanism could improve recasting on speed and accuracy and reduce fatigue. Second, bubble ray A had higher selection speed and good user experience. Third, our evaluation in general cases were trivial. Advanced recasting techniques like heuristic ray, quad cone, and two bubble rays all have good and stable performance whatever the scenes change. This motivates us to evaluate them in more complicated cases. So we conducted the second experiment. The second experiment included 3 extreme cases: high density, high occlusion, and density and occlusion. In high density scene, there are 7 by 7 targets in a dense matrix, and the margin between targets is very limited. In high occlusion scenes, 4 targets are behind a large distractor. That means 4 targets behind is occluded by the front one. In density and occlusion scene, there are 5 by 5 by 5 targets in a cubic layout, so the inner targets are both dense and occluded. We also recruited 12 participants and built the platform in HTC Vive with Unity. In this, we evaluated 5 recasting techniques in this experiment. That is Naïve Ray, Heuristic Ray, Quad Cone, and 2 bubble rays. In high-density scenes, bubble rays degenerated into Naïve Ray, so their error rates were as high as Naïve Ray. In high occlusion scenes, bubble ray E becomes awkward because the distractors always be the nearest one in Euclidean distance. However, angular distance didn't have this problem. In density and occlusion scenes, all recasting techniques had higher error rates, except quad cone, because it had a disambiguation step to increase the robustness. In general, we can find that bubble ray A had a higher selection speed, but in dense scenes it became error-prone. There are several findings. First, angular distance is better than Euclidean distance. Second, in dense scene, due to the temporal model in heuristic ray, it will be sticky that attaching the ray on the target and solve the hand tremble problem. Third, from the post-experiment talks, users prefer the quad cone in these extreme cases because users pay more attention to the success rate rather than the speed when the scene is complicated. We propose some improvements over the bubble rays as our future works. First, we have speed surrounding dependent bubble ray. In sparse case, the bubble ray remains the same, but in dense case, or when the user's rate is slow, it becomes a sticky rate to make less selection errors. Or we can combine the gaze with the bubble rays. With gaze, we can only consider targets within the user's gaze region to avoid some unintentional selections. Alright, thank you for listening.
Hello everyone, my name is Roberto Montaño. I am a postdoc at Interact Lab in the University of Sussex in the UK, and today I'm going to present a...
All right, everyone. I want to remind everyone that we have time for questions, and those are posted on Slido under the IEEE VR 2020 link. So if you have questions for Ichin, make sure that you post them on there. As we're waiting for questions to come in, I guess I could start out and ask you one. I noticed that in one of your videos, you had a this was the ray bubble ray version 3, where you're drawing the ray on the hemisphere. When you look down, it looks like it still jumps. What do you do when you're trying to select targets that are in front of the floor, essentially?
Actually, we didn't evaluate the target on the floor, but I think, but we propose. Sorry, can you hear me? We propose the advanced technique that bubble ray plus bubble cursor that will solve this problem. That if you select near or some targets that are not in the remote distance, then you can use bubble cursor.
Great. Are there any other questions from the audience? Let's see. All right, I'll ask another one while people are thinking about it. So you do slightly different things in dense data sets versus more sparse ones. Do you think that it's jarring for the user to kind of swap between the different visual feedback in terms of having a sticky cursor in really dense versus not?
So you are asking that user are switching from techniques, or?
Yeah, so switching between them, is that jarring to the users?
So I think we should design a smooth transition to avoid avoid switching, because the user from our study, the users are more responsive, that they find that the performance is not the most important. They think that the user experience is the most important. So we should design the transition to make this process so more smooth is most important.
Okay. Let's see. I think we might have one more question, but I'm waiting for it to actually show up on Slido. Interesting technical issues with having an online conference. Apparently the Twitch stream is showing the wrong Slido channel. Is that? All right. Well, in the meantime, why don't we take this offline, and those of you that have, let's see. Oh, maybe one came in. So a question from Francesco Ortega. It said, you mentioned significant findings using ANOVA, but was the data normal, and what was the effect size?
It's our limitation. We didn't test the normality, and we can we can report the effects, but we just report the significance. This limitation of our paper.
Okay, thank you. Let's move on to the next paper then. So our next paper will be titled Improving Obstacle Awareness to Enhance Interaction in Virtual Reality. And this will be presented by Manuela Chesasa.
Hello, everybody. Do you hear me? Can you hear me? Do you hear me? Okay. Should I start? Okay. Hello, everybody. I am Manuela Chessa from the University of Genova, Italy. I'm presenting our work to improve obstacle awareness to enhance interaction in virtual reality. The motivation of our work is well known. When we are immersed in virtual reality, the real environment around us can be dangerous. It did when we move in the real environment by wearing a headset, we can hurt with obstacles that are around us. In the literature, there are several possible solutions. One of the most known is the one available on Steam VR. For example, we can enable the pass-through mode of the camera in front of the headset, and we can have a representation of the edges and of the boundaries of the objects around us put inside virtual reality. The solution works, but of course, what we have is something that we wouldn't like to see inside virtual reality, since we have some sort of out of context information put inside virtual reality. For these reasons, several other solutions have been proposed also recently in the literature. One is inspired by the previous explained one, and we can collect information from the surrounding environments and put a representation of the obstacle in the form of point cloud inside the virtual environment. Again, this solution is okay for obstacle avoidance, so we can avoid to hurt obstacles. But again, we have a sort of out of context information, so we see in virtual reality something that we wouldn't like to see. Again, recently, for example, at ISMA 2018, other solutions have been proposed, for example, to put objects that are detected in the real environment inside the virtual one. But again, the problems remain. The goal of this paper is to try to improve obstacle awareness without losing contextualization, thus without losing the sense of presence. In principle, what we would like to do is to detect obstacles in the real environments and to put virtual obstacles inside the virtual reality environment. And what we would like to have is a sort of virtual obstacles that are contextualized with respect to the virtual environment that we are exploiting. This approach, on the other side, will lead us towards augmented virtuality, to allow physical interaction with real objects being immersed in virtual reality. For example, if we have a real chair in the real environment, we can put into the virtual environment a virtual chair, and eventually we can sit down on the virtual chair. The method that we have developed is to create a virtual reality scene consistent with the presence of objects in the real environment. Let's start from the beginning. We start from a real cluttered environment like the one that we can see in this slide. So we have a lot of objects in the real environments, and these objects could be real obstacles. Then we can acquire a 3D scan of the real scene. Our method works with any 3D scan acquisition, so any 3D scanner and any software. It is not important if we have holes, since the method is capable to cope with the holes. And also low resolution is not a problem since we will have low resolution in the final result, but the system could work as well. Our development method is not real time, since it is thought to be a pre-process before using the virtual reality. After we have the 3D scan acquisition, we compute a voxelization. To compute the voxelization, a matrix of checkers scans the scene. At each collision between the matrix of checkers and the 3D mesh, a new voxel is instantiated, of course, at the position where the collision occurs. We can change the number of checkers per side, so we can improve the accuracy of our method, and we can also increase, of course, the execution time. The maximum intersection represents the floor. So when we have the maximum intersection, we can put a floor in our model. After having computed the voxelization, we have to clusterize the scene. So adjacent voxels are grouped together. To do this, a sphere around each voxel is defined, and the connected voxels are merged together in a recursive way. Thus, we obtain a clustering like the one that we can see in the figure. The last step is to build the virtual reality scene. We take objects from a pre-built library, and we instantiated such objects in the virtual reality scene by changing their position and their occupancy accordingly with the previously determined clusters. So the clusters that come from the previous step, the clusterization step. The last step is to align the virtual reality environment with the real environment. To do this, we take into consideration at least 3 points that should be present both in the real environment and in the 3D scan. In our implementation, we are currently using the 2 ATC5 base station and 1 tracker of the ATC5. Let's see another example. For example, an office lab space. We start from our lab. This is a snapshot of our lab. And this is a video of our method when it works. We start from the floor detection. So we see the matrix of checkers that scan the scene, and we detect the floor. Then the same matrix scan the scene from the top to the bottom, and we perform the voxelization. We see in this case the voxelization with 70 voxels per side, and then the voxelization with 100 voxels per side. In a few seconds, I will explain to you the difference. Then we perform the clusterization, and the last step is to build the virtual reality scene, and the user is now inside the virtual environment, and we will see our evaluation in the result. Let's focus for a while on the result and on a small detail that is present in the scene, for example, the detail that you can see in the photo in the middle of the slide. We can see that by considering 70 voxels per side in the scanning matrix, we are not able to voxelize this object, whereas by increasing the number of voxels, we are able to perform the voxelization of the objects and then the clusterization, so we can detect and represent also the small objects in the final scene. In our method, we can also put additional checks. One is to perform a tiny voxelization instead of a voxelization. So instead of instantiating 1 voxel at each collision, we can instantiate a sort of pillar, so a sort of parallelepiped going from the first collision toward the floor. By doing this, we are able to instantiate less objects. That plays an important role when using Unity 3D. But on the other side, we lose some details in the scene. For example, we lose holes in the scene. Also, for what concerns clusterization, we can add an additional check on the height, so we can clusterize, like in the bottom part of this light object, by taking into consideration that some object could be composed of different objects, one above each other, like the example of the display that is above the desktop. Coming to the results, first of all, we have analyzed the computation, the time to compute the voxelization and the clusterization, so the time to create a virtual reality scene starting from a 3D scan. I have already said that the approach is not real time, but it is not required, since the virtual reality scene is created offline. Of course, when we increase the number of voxels per side, we also increase the time necessary to compute the scene. And in order to be able to interact with the scene, we should act as a form of tracking in order to be able to move objects, but it will be part of a future work. About the user experience evaluation, we are now seeing an example of a user immersed in our environment. You can see that the user is able to freely move inside the cluttered real environment and is seeing obstacle when is obstacle that in this case are just stones when he is approaching the real obstacles. One example is when he saw the small obstacle on the floor. We asked the users to reach the obstacle, so to reach the small stone on the floor, to touch the obstacle by using the ATC Vive controller and to put the ATC Vive controller on the obstacle. And you see that in this case, interaction could happen in quite a accurate way. Then the user can continue to walk around in the environment. And a last example of interaction is when we asked him to reach and touch what in the real environment is the display. And also in this case, the display is represented like a stone. And again, the user is able to touch what is in the real environment, the display, the monitor of the PC, and in the virtual environment is a stone. We performed a preliminary evaluation by taking into account 6 participants, and the task is exactly the one that we have already seen. We use the ATC Vive system, a cluttered real room that is more or less 2 meters by 3 meters. The task is to explore the scene for 5 minutes and getting close to obstacles. We consider the I-group present questionnaire to evaluate and to assess the sense of presence by comparing our developed system with the standard Vive chaperone boundaries system. And about our system, we consider 2 implementations of our method, one with the standard clustering and the other one by adding the constraint on the height. What we can see from the result is that our system outperformed the Vive chaperone system with respect to all the domain considered by the I-group presence questionnaire. So by considering both involvement, realism, and spatial presence. And coming to the conclusion, we have, starting from a 3D scan of the environment, we have developed a method to voxelate the 3D scan with the desired accuracy, to clusterize adjacent voxels and create bounding boxes of separate objects in the 3D scan, to compute the position and the occupancy of each bounding box, to put a virtual object from a pre-built dataset in the same position and with the same occupancy. We have proved that we have shown that the method works with any cluttered environment, any 3D scan hardware and software, and that the system allows us to avoid collision with real objects, providing a better sense of presence to the users with respect to a standard technique. Of course, the method works offline and can be used on static scene only. But our plan is to go towards augmented virtuality. We have shown that we can reach the virtual object and touch the real corresponding one. In the actual implementation, we have considered only a set of stones with different shapes. As future implementation, we see that a dictionary of different objects and a semantically consistent replacement via ontologies could be implemented. So by replacing real object with something that has similar semantic behavior in the virtual scene, for example, to replace a real chair with a virtual chair, or a real standing obstacle with something standing in the virtual reality. And another improvement is to track real objects and corresponding virtual ones to allow interaction. So to allow people to reach the objects, grasp the objects, and eventually move the objects. Thank you for listening, and I will answer to your questions, and you can write to me and also reach me via Twitter or via via email. Thank you very much.
So thank you. Very interesting work. We have a lot of questions actually in Slido. The first one is, do you think that there might be a problem that users confuse real and virtual obstacles in this approach? I.e., can you walk through some obstacles but not through others?
Yeah, indeed, it is also part of the future work. In this case, we have just replaced the real obstacle with stones, and the answer is absolutely yes. What we can do is try to exploit the presence of real obstacle, not only for obstacle avoidance, and in this case, confusion could happen, but also to allow people to touch the virtual obstacles and have the tactile feedback of the real one. And to do this, of course, we have to take into consideration the semantic of the real obstacle and to try to build something that a semantic approach to the environment.
Yeah, just a kind of a quick follow-up on that. I could see that you might even be able to elicit specific behaviors, like if you replace an obstacle with something like a soccer ball, where there is a very clear interaction paradigm. You might be able to get people to kick the item,
yeah,
right? That sort of thing.
Of course, we have not to do this. Yes, of course, it is dangerous, and with semantic substitution, I of course also we should also consider this.
Yeah. So the next question is, can you elaborate about the limitations caused by scan quality? If we had a better scan, would that enable you to overcome some of the challenges? And so what is the general terms of quality we need in terms of scan for obstacle awareness in general?
Yes, for obstacle avoidance, a poor quality in the 3D scan could not be a problem, since what we would like to do is to avoid collision, and our implementation also consider very poor 3D scan, and what we do is a bigger clusterization. So we have a bigger cluster, and we can consider a real obstacle bigger than they are in reality. So obstacle avoidance is of course preserved. But of course the scene is the virtual scene is in a certain sense more dense. So we build a more dense virtual scene. If we want to go towards interaction, of course, and so we would like to explore the presence of real objects to touch, to reach them, to touch them, and to grasp them, the 3D scan should be more accurate. So the clusterization could not be bigger, but should fit in a more precise way the real objects.
I think your video may have broken up a little bit there at the end, but that's okay. Another question is, someone was wondering whether you plan to utilize this mapping of the physical environment onto the virtual environment to implement passive haptics, similar to work by Alberto Simone et al.
Sorry, I haven't heard you. If you can repeat, sorry.
Yeah, so someone is wondering whether or not you plan to utilize this mapping of the physical environment onto the virtual to implement passive haptics, as well as just avoidance.
Yeah. Exactly. Instead of using just avoidance, it is a method to have passive haptic.
Okay.
Yeah.
We are running a little bit short on time, so there are a couple more questions that I would ask the participants just ask in Slack, and maybe you can get on Slack later to help answer those. So, all right. Thank you very much. Very interesting.
Thank you very much.
The next talk is titled Slicing Volume, Hybrid 3D, 2D, Multi-Target Selection Techniques for Dense Virtual Environments. And this will be presented by Roberto Montano Morello.
Hello everyone, my name is Roberto Montano. I am a postdoc at Interact Lab in the University of Sussex in the UK. And today I'm going to present a project I did during my internship in Adobe Research. Slicing volume, hybrid 3D, 2D multi-target selection technique for dense virtual environments, which is a working collaboration with Kwon Nguyen, Rubaiyat Habib, Stephen DiVerdi, Sriran Subramaniam, and Diego Martinez. Current 3D scanning technologies allow us to capture more realistic and detailed pieces of the real world. This is increasing the amount of 3D scan content that we can have access to. For instance, in the current video, the amount of points in the model could be really high. For instance, maybe over 6 million points. In these kind of dense scenarios, target selection becomes crucial to work with these point clouds in tasks such as cleanups, analysis, and editing. However, if we try to edit a point cloud in 2D, for example, selecting points using your mouse, this task becomes extremely challenging because the environment is too dense, and this task is highly dependent of the user viewpoint. And this means that you need to constantly rotate and translate the environment to get the proper view to allow you to select the points you wish, no more, no less. One possible solution for this problem is to translate the 3D data into the 3D virtual environments, such as using virtual reality. This is because VR allows interactions using the 6 degrees of freedom controllers that enables a more natural and intuitive interaction that can be reflected on 3D object manipulation, data manipulation, and in the case of our research, selection tasks. But even when VR approaches for 3D selection provide advantages, the selection task itself remains challenging because the model density or the scene density, and of course the occlusion problem. But also, when using these VR controllers, there is an implicit lack of stability in accuracy demanding tasks. I mean, tasks that require high level of movement precision, for instance, a precise multi-target selection in a highly dense and occluded environment, such as in the video. Producing over-selection, selecting more elements than the target, and under-selection, selecting less elements than the target. Additionally, mid-air interactions may be tiring for long periods of time. To solve this problem, additional methods have been proposed in the literature to visualize 3D data, including additional viewpoints using virtual cameras and using additional manipulation tools to ease the 3D data exploration, maybe using tablets, by taking advantage of the slicing plane or cutting plane approaches, visualizing the cross-section to allow users to control the plane view across the 3D data. In our paper, we got inspired by the use of tablet in VR approaches and slicing plane techniques to address the 3D selection problem in highly dense virtual environments, such as selection in point clouds. By combining these two approaches, we obtain the advantage of the stability provided by using a physical surface, for instance a tablet, and the extra visualization that cutting planes can offer. Therefore, in this paper we propose slicing volume, a hybrid 2D 3D selection technique tailored for highly dense and highly occluded unstructured data in VR in real time. Our technique maps the complex 3D target selection task into a hybrid workflow that combines both mid-air and tablet interactions. We conduct a user study to understand the factors influences the user performance in 3 independent factors: the use of extra visualization, physical support or stability, and the level of task complexity. Slicing volume defines a region in the 3D space to be mapped onto the 2D tablet view in VR. Contrary to slicing planes that usually visualize the cross-section of the data, the slice, slicing volume uses an orthographic projection of a virtual camera to capture the content enclosed within this volume, but not the neighboring elements. The rendered view on the tablet surface allows users to have a visualization tool to filter out elements that surround the desired target selection, intuitively handling then the occlusion problem. The dimensions of the volume can be dynamically adjusted by using the joystick on the left controller, allowing users to customize the 3D space mapped on the current virtual tablet view. For example, increasing the thickness of the volume facilitates the selection of a larger set of points, while decreasing the thickness facilitates the precise selection of occluded points. Our technique is based on bimanual interaction methods and employs pen and tablet metaphors. As you can see in the video, a real tablet is attached to the left controller using an adjustable 3D printed holder. Then, a physical stylus is attached to the right controller for touch input on a physical surface. This is an example of how our technique works. The user places the volume, which is initially attached to the virtual tablet, on the desired area in VR. Then adjust the volume size and thickness to explore the model and manage occlusions. The points enclosed within the volume are projected into the virtual tablet view. Then the user selects the points on the tablet surface using a pen and tablet metaphor. The selection on the tablet is then propagated along the slicing volume thickness and is updated on the 3D model. When touching on the tablet, our technique casts a ray from the touch point perpendicular to the tablet surface to select all the points along this ray, which length is defined by the slicing volume thickness. Thus, users can select 3D points using continuous tactile touch, following the pen and tablet metaphor, which is physically more comfortable and precise. We conducted a within-subject user study in VR with 12 participants to test our system. Our study aimed to, first, explore whether our approach improves user performance in selection tasks, and second, gain insight about the cause of potential benefits obtained during the user study. For instance, if the benefits came from the extra visualization or from the haptic feedback. We designed a dense point cloud environment for our user study. The point cloud model consisted of about 1 million points. The model shows a museum with 3 sculptures, a statue, a T-Rex, and an elephant. The statue was used just for training users. The T-Rex and the elephant were used for the main tasks. Each model has a set of target points highlighted in orange. The target points were distributed in geometric patterns. Each model represents a different level of difficulty, defined in terms of level of occlusion. In this paper, we define the occlusion level by the average point density per space unit. For instance, the elephant model has an average density of around 22,000 points per space unit, containing around 7,000 target points. Then, the T-Rex model has an average density of around 42,000 points per space unit, containing around 20,000 target points. This means that the T-Rex model was almost 2 times more occluded and therefore more challenging than the elephant model. 3 different conditions were tested in this user study. In midair only, participants used the right controller to select and deselect target points by brushing in midair. In virtual tablet, in addition to this mid-air selection, participants were also allowed to use a slicing volume tool through a virtual tablet. Because this mode doesn't involve any physical tablet for selection and deselection, we employed a virtual laser attached to the right controller to interact with the virtual tablet, but without haptic feedback. In the real tablet condition, in addition to this mid-air selection and virtual representation with the slicing volume tool, participants were given an iPad Air tablet which was attached to the left controller and a physical pen attached to the right controller to allow selection and deselection of target points with an additional stability and haptic feedback. This is our setup. Participants were asked to sit next to a semicircle-shaped table and they wore an Oculus Rift headset. On the real tablet conditions, participants were allowed to rest the real tablet on the table to avoid fatigue. In all conditions, participants could translate and rotate the whole environment to interact with it while sitting, to avoid overstretching. To test our technique for each condition, we measure accuracy, using F1 and MCC scores, over-selection, which is the number of points selected that do not belong to the target, under-selection, which are the number of points not selected that belong to the target, time, which is the time the participants spend selecting, deselecting, and the total time, and task overload, using the raw NASA TLX scale. In the results, we found that participants' accuracy depended on the occlusion level of the model. For example, we found no difference in accuracy across the three conditions when participants were interacting with the elephant model, the less occluded. However, in the T-Rex model, we found that in real tablet condition, participants were significantly more accurate than in mid-air condition. But even when virtual tablet condition also outperforms mid-air condition, the difference was not statistically significant. This suggests that the physical surface in the real tablet was clearly beneficial due to the extra haptic and stability support. In terms of under-selection and over-selection, our results show no benefit of the tablet conditions, virtual and real, when selecting the elephant model. However, for the T-Rex model, we found that only during the real tablet condition, participants over-selected significantly less than during the mid-air only condition. This suggests that in terms of over-selection, participants benefited more from the physical tablet surface thanks to the stability rather than having an extra visualization given by the slicing volume tool. In terms of under-selection, for the T-Rex model, during both conditions, virtual and real tablet, participants significantly under-selected less compared with the mid-air only condition. This suggests that in terms of under-selection, having an extra visualization given by the slicing volume tool helps to improve participants' performance rather than having haptic feedback given by the physical tablet surface. In terms of time, we found that participants spend more total time in the real tablet condition. This could be because of the extra maneuvers that participants executed to look at the tablet and adjust the volume thickness. However, total time was only significantly higher when selecting the elephant model, involving lower points density. This suggests that our hybrid system is more effective for higher dense models, improving accuracy without significantly increasing the task completion time. One interesting observation in our result is that overall, participants took more time of selection in the mid-air only condition when selecting both models. This means that even when participants took more total time during the tablet conditions, they spent significantly more time in selection mode during the mid-air only condition. This suggests that participants could select target points faster and felt more confident about their selection, spending less time selecting, thanks to both stability and extra visualization provided by the virtual and real tablets. Regarding participants' load index, we observe a trend showing higher scores for the real tablet condition, but it was not significant in most of the cases. However, we found that participants perceived significantly better performance when using the real tablet. To conclude this talk, in this paper, we presented a novel hybrid interaction technique called slicing volume for selection in highly occluded point cloud models in VR. Our approach provides users with a 3D volume visualization that can enclose target objects in midair. Users can employ this volume to inspect and filter out potential target points for selection. These points are then mapped to a 2D tactile tablet surface so that users can select with additional haptic feedback. We tested our system in a user study and found that our interaction technique improved the accuracy of selection in highly occluded point cloud models in VR. Our results also provide insights into specific benefits of our technique. We found that the mapping 3D to 2D is generally the most beneficial when it comes to aiding the selection. Overall, these findings show that our technique can act as an effective tool to help users inspect and select target points in dense virtual environments. This is all for this talk, and thank you very much for your attention.
Well, thank you. Just as a reminder, please submit your questions on Slido. And we have one question there already, which is, why do we need a real tablet? Wouldn't a smooth pane and a stylus plus the controller tracking be enough for passive haptic feedback?
Well, that's interesting. First of all, as humans, we have inherent limitations. For instance, have you used steel brush before?
Yes.
This drawing in VR.
Mm-hmm.
So usually this kind of drawing or selecting is highly dependent of the viewpoint. So what I mean is that if you try to draw a cube in VR, so you, from your perspective, this cube will look amazing. But whenever you start looking around, maybe it's not even connected, the line. So the thing is that from this perspective, we can have an increment in stability or in accuracy when drawing, let's say. But this additional stability is provided by a physical surface. So, and we test in our user study that this additional surface is also providing, this additional stability is also increasing the accuracy when selecting. And using a real tablet can also provide an additional touch input that can give us more accurate intuitions about zoom in, zoom out, or selecting just brushing on top of the surface. So
yeah. So just to clarify a little bit, they're wearing a head-mounted display, so they can't actually see the tablet. So you're mainly using it to track the input.
Yeah. Actually, that's exactly. So the tablet was attached to the left controller. So basically, we were tracking the controller, and the virtual model was attached to this tablet. So we were using the real tablet just to record the touch events.
Okay. So the next question is, can you provide a little bit more information about the architecture you're using and how you communicate between the tablet device and the HMD?
Actually, we're using Unity and HTC. We have two versions. So we started using HTC Vive, but actually, as we did implementation using Steam, so we can use both Oculus and HTC. And we're using this network transport, I think is the name of the communication between the tablet and Unity. So it is the native communication is working quite well. And all the implementation was done using shaders. So the thing is that when using Unity, you have a maximum number of elements, interactive elements that you can actually render, 1,000, a bit more. And the thing is that right now we have over 1 million points that you can actually interact with. So we're doing this using shaders. So we are computing all these interactions in the GPU in order to allow users to edit elements in a point cloud in real time.
Interesting. So the next question would be, did you experience any break on immersion during the study when using the real tablet?
Actually, that's interesting. I remember a comment from one of my participants, and this participant was saying that it was interesting because even during the task, this feeling of having a physical surface on the hand, it was keeping the accord to the real world, and that's probably is breaking a bit the immersion. But however, I think that's also an interesting point to look at. So when is this accord to the real world necessary? So yeah. Future work.
Right. And someone is asking, what did you use, which sensors to track the items, tablet and pen, not typically in a VR environment? How is latency optimized for large volume data, and how to affect the selection?
Can you say it again, please?
So what sensors were you using to track the tablet and the pen, and how was latency optimized?
Okay, yeah, actually we're using just the Oculus controllers. So we wanted to keep it simple because our main goal was to check the difference between our conditions, our modes, and we wanted to keep the number of tracking system or tracking technologies as simple as possible, avoid over-instrumenting the user, so in order to get only the necessary information we need. But actually, We have some more sophisticated versions of this software in this project. However, right now, the user study was done with just naive participants, and we are aiming to have a second experiment with expert participants, expert users that can actually explore in more detail the advantages of the tool.
Interesting. And the final question is, how do you overcome the limitation on the orientation of the tablet? For example, do you have to rotate it if you want to see the points that are on the left side of the elephant if you're looking on the right side?
Well, yes. There is a limitation in order for users to automatically recognize the position and orientation of the cube. But actually, if you saw it during the video, there were a kind of coordinate system representation in both the tablet and the cube in the space. So you can actually just by visualizing the cube, you can automatically match the orientation in the 3D wall.
Yeah, interesting. All right, well, thank you very much. We're gonna close down the screen as we shift to the next presenter. And in the meantime, all right, we're back with our final paper of the session, and this is an invited TVCG journal paper entitled Entropia Towards Infinite Surface Haptic Displays in Virtual Reality Using Encountered Type Rotating Props. And this will be presented by Victor Mercado. Victor, we're not getting sound for you. Could you turn on your microphone? We're having a few technical difficulties with the sound, so we'll be back in just a second.
Okay, let me just go back. Well, as I was saying, thanks a lot, Brett, for the nice introduction. So let's begin again with the basics. So just talk about encounter type haptic displays, which is basically the main domain of this contribution. So what are encounter type haptic displays? Well, basically, they are hi-fi robots. So these emotionally needy robots, actually what they are going to do is they're looking for the position of the user's hand in order to provide a surface so the user can actually encounter the surface and thus gain haptic feedback. The premise is actually pretty interesting because in contrast with other type of haptic interfaces, the user do not have to wear an actuator right below the user's skin. So that we have a more natural haptic feedback that can be rendered in virtual reality. So that's basically the main premise of encounter type haptic displays. So everything looks fine. Everything seems interesting for these devices. But at the end, the issue that we have is that we have a limited contact area. For instance, as you can see here in the work of Araujo et al., the contact area is actually limited to one of the sides of the prop. So we cannot have more than that. Of course, we can rely on positioning algorithms in order to replace the position in order to touch a surface that is actually bigger than what you see in the virtual reality environment. But at the end, we're limited in matters of the physical size of a prop. So we propose a novel approach for this, which is called encounter type rotating prop approach, and thus the name Entropia, which is basically optimizing the rendering area of ETHDs. So basically what we're going to do here is just to exploit the shape properties of a cylinder to render a large contact area, in this case, a large flat contact area. So this is basically the main approach, the main premise of Entropia. So the contributions of this paper are the entropy approach, but also a proof of concept for integrating entropia into a use case and apply use case. And we also have a user study in order to test the effectiveness and performance of entropia against the state of the art. But what is the state of the art? In this type of ETHDs, first we have the grounded type, which is basically just grounded robots. And as you can see in the video here, we basically rely on grounded robots that provide multi-texture rendering, which depends again on a physical prop. So for instance, here, the work from Posset that provide different surfaces that are just represented in a virtual simulation over here. And it's actually a pretty interesting premise for grounded ETHDs in particular. But we also have ungrounded ETHDs, which are basically using drones and mobile pin arrays in order to have a wider workspace area. So for instance, here we can see Abtahi and how she's touching a contact area that is being rendered using the drone, which is a pretty interesting premise as well, because the workspace actually becomes quite bigger. And we have other types of shape displays. For instance, this one is a pin array. And Abtahi and Fulmer are actually using visual haptic illusions to increase the performance of the haptic rendering as well, increasing the resolution, scaling, just to profit from the capabilities of this mobile pin array. And we also have a very interesting work, which is the haptic revolver by Whitmer et al., which follows a premise that is quite similar to Entropia, which is basically this round surface that is being spin under the user's finger to render haptic feedback as well. and you can see that it renders haptic feedback in a continuous fashion. But of course, at the end, there are limitations for these approaches as well for the ETHDs. Primarily for ETHDs, as you can see, there's, as I mentioned before, a limited contact area, but also haptic rendering time. There's actually the elapsed time that the robot takes to get from one position to another. And we also have to consider that this cannot be like super fast because there are safety issues as well. And of course, we are limited in matters of texture rendering because not all ETHDs follow this premise. And for holdable devices, such as the haptic revolver, we have the constraint that we have to hold something, and then we only have to render haptic feedback over a very small area. So basically, that's it. So let's just talk a little bit more about the approach of Entropia, which is pretty simple, actually. So basically, you can read the whole slide, but I just have a visual illustration here. So basically, the thing is that we are just going to optimize the contact area by just profiting from spinning a rotating surface under the user's finger. So at the end, we can actually optimize the contact area, and we can have a large flat surface rendering using Entropia. And not only that, but you also profit from the cylindrical surface to put more textures over there. But of course, this cannot be achieved, but without the an interaction technique, which in this case, for instance, it's 3 phases. The ready phase, just for telling the user, be ready, just start touching the prop. And then we pass to the touch phase where the contact area becomes blue. And as you can see, the user is actually following and being in constant contact with the contact area for rendering the actual haptic feedback. And at the end, there's another phase for prompting the user to release contact with the surface. So in a proof of concept, what we use to implement the whole thing, we use a universal robots UR5 robot. And we hold as well here the Entropia prop, but we also use the Vibe system to render the virtual environment, and the tracking system as well to acknowledge the user's position, the position of the Vibe controller, and the user's finger as well, because this is the element that we're going to render in the virtual environment to represent the user. So let me show you the video of the proof of concept. So as you can see here, there's a virtual scenario, which is basically a virtual desktop with different textures that the user can explore. So as you can see here, the user can actually select a texture that can be touched. So in this scenario in particular, we have 3 different textures that can be touched. It's wood, paper, and we also have leather. So as you can see, the user is actually following the instructions of the interaction technique. You can see there the contact area, which is being represented under this little square. And then the user is actually profiting from the interaction technique to explore in matters of haptics, the contact area or the virtual desktop. So of course, we have implemented this. And at the end, we have also our user study in order to compare this approach against the state of the art. Basically, that's the objective of the user study, just to compare and assess the haptic perception that is given by Entropia, compare it against the state of the art, with a hypothesis of having Entropia to be an optimal solution for rendering a large contact area. So therefore, we designed an experimental prop for comparing these conditions. So here you can see the prop more in detail. So first we have the first stimulus of the experimental trials, which in this case was the ground truth. So it's represented by a large flat area that we actually want to render with the other approaches. So there was a combination of the ground truth versus the translated rotating round surface, which in this case is Entropia. We have the state-of-the-art conditions that we consider 2 in particular: the translated flat surface and translating round surface. So these combinations of stimuli were ordered in inter-experimental trials in random order, 10 trials per stimuli combination. So I will show you a video about the user study. So first we have here where the user is actually touching the ground truth, or basically the reference that the user is actually going to use for comparing it against the other approaches. So as you can see, the virtual environment is basically just a flat surface, and we have the interaction technique for getting the user in the moment of exploring the surface to be touched. And then we have, for instance, we have Entropia as well, with the condition of the round rotating surface, and that is also translating as well for rendering the sensation of touching the flat surface, and the state of the art as well. which is represented over two conditions. The first one was just touching a translating round surface, as you can see. The user just touched a little part of the prop, the one that is round. And we have another one for the translating flat surface as well. And basically those were the conditions. So after the second stimulus, the second stimulus, we asked the participants to evaluate in a 7-point Likert scale whether they perceived differences between the two stimuli, and they have to evaluate this, having to say if that was completely different or completely similar in a 7-point Likert scale. So that was during the experiment. That's our quantitative data. They collected data in matters of subjective questionnaire. We asked the participants at the end of the experiment if they felt that motion, speed, or curvature were important for them for discerning between the two stimuli. And we considered a population of 12 participants as well. So the results, in general, on average, Entropia provided a sensation closer to touching the ground truth. In second place came the translated flat surface condition, and in third place, the translated round surface condition as well. So we ran a statistical analysis based on analysis of variance, and we found the statistical differences between the three conditions. So basically, those are the main results that come from Entropia as well. But of course, considering the subjective questionnaire, participants marked that motion was also the most influential factor for the differentiating the stimuli. And at the end, there's a lot of things to consider, because even if, for instance, this user study actually proved that Entropia can render a sensation that is closer to the ground truth, at the end, there's a lot of things we have to tune. We have to tune as well the angular velocity. We have to take into account the prop radius that might just vary from user to user, because the size of a fingertip, of course, it has also a lot of influence in matters of haptic perception as well. And of course, we cannot enlarge the contact area that much because the robot has to displace this huge prop. And what I actually want to do is just to optimize everything in matters of the size of the rendering prop. And of course, friction and pressure from the users influence a lot on the haptic perception and for differentiating touching the ground truth against, for instance, entropic condition. And this also interferes as well for the haptic perception. And those are things that we have to consider for optimizing Entropia. So in conclusion, we presented this rotating prop approach, which is called Entropia, but it's not only the approach per se, it's also the interaction technique that actually facilitates the user to explore this virtual surface. And we also create a proof of concept, which integrates the Entropia approach for rendering multiple textures in a virtual environment. And we also made a user study that proved that on average, Entropia provides a close sensation to touching a flat surface. And in matters of future work, as I mentioned a little bit in the discussion, there's a lot of things to do in matters of haptic rendering. We can also study more about the radius influence on the Entropia approach, the capacity as well to render curved surfaces. Perhaps we can apply Entropia to ungrounded ETHDs, not only for optimizing the contact area, but also the workspace of the ETHD. And of course, we can create new interaction techniques, which is going to be also a topic of discussion in a further presentation that I'm going to give on session 7 haptics Tuesday. And also new applications for Entropia as well, mostly focus on industrial design in order for doing like fast prototype of different environments of work that could need for the users to explore with the sense of touch surfaces that can be fastly prototyped as well. And all of this is just the effort to move towards infinite surface haptic displays, which basically, as the title mentions, basically this kind of haptic devices are the ideal ones, which are basically the fully optimized haptic experience. And of course, I want to thank you for your time. Thank you for listening. And if you've had any question, then feel free to answer. And I will just leave you with the video. And here's my mail if you want to contact me as well, if you had any questions or further comments.
All right, thank you. Let me just check Slido. It looks like we don't have any questions there yet, but if the audience does have questions, make sure you submit them on Slido.
Okay.
I'll start. So I have to admit I'm not that familiar with these types of robotics. It seems like you would be really limited on the speed of the type of interaction. Like, so in your videos, it looked like, you know, the person was moving their finger very slowly along the surface. What are the constraints for that?
Well, in matters of, this is a pretty interesting question because I think that there are two variables at the moment that influence a lot. One is safety, because if for some reason the user have a collision with the robot, there's going to be a huge impact that might be just in the users. And the other one, of course, I think it's friction. Friction also is very dependent on the speed of the robot as well. So we don't want it to spin the prof in this case like super fast, because otherwise we might disclose that there's something going on over here that is kind of suspicious. So I think that's what I mentioned that in future where we might try to tune a little bit more about the matters of speed, of course, angular velocity, and take into account not only the matters of friction as well, but of course texture, that all of those things are super related. So yeah.
Do you find that the robot makes sound that might break the presence or somehow indicate to the user that something's going on?
Definitely. And unfortunately, I didn't mention that here, and it's not in the diagram, but it's mentioned on the paper. And you can be sure that participants also used a headset that played white noise in order to isolate them from the noises of the robot, because yeah, actually the robot is kind of noisy, but do not worry, we use the proper precautions as well, because yeah, I even have to wear a headset as well when I'm working with the robot, because yeah, it's kind of noisy.
Yeah. All right, we have a question from Slido, which was nice work. Do you think Do you think changing the disk's rotation, it might be possible to simulate different materials with one physical? So, for example, could you do uneven or bumpy surfaces?
Okay, that's a pretty interesting question. And then again, I think it's super related as well, not only with matters of rotation and angular velocity, but of course with the texture as well. So yeah, it's a matter of just trying to tune these parameters. I really think so. I'm not going to disclose that much, but perhaps that's something that we are working on. So yeah, because you're actually interested on simulating curved surfaces as well with entropia. So yeah.
Yeah, there's another question along those same lines, and I think it's be very interesting to see where this goes. So,
cheers.
Yeah. Well, if there are no further questions, that concludes our session, and I will remind people to the next session is posters and video, and make sure you stop into the hub rooms and look at the sponsors as well. It's really great that they stuck with us as we move the conference online. So thank you all the presenters, and thank you audience for your questions. Thank you.